Hello, and welcome back to Paleozoic PCs. So today, in part 3 of the homebrew video card project, we're going to try to be a little more coherent in talking about things. So first off, I'd like to apologize for the terrible audio quality of the last video. Apparently, the microphone wire that I'm using has been picking up a 60 hertz hash from a little desk lamp, and I thought I had managed to get rid of it, but apparently my monitoring was not set up correctly, so going to at least try to do better today. Anyway, so here we are, and got the video demo running again. You'll notice something different on the oscilloscope. I'll explain that in a minute. One thing I want to just throw out there quick about one of the advantages of using a microprocessor for the timing is it is possible to fix things simply in software that would be harder to fix in hardware. One of the things I've noticed is I've seen some of the videos recently from the 8-bit guy talking about a machine called the Mini Pet, which appears to also use an Atmel CPU for address generation. And one of the complaints he's had about it is that the video is all offset to one side. Now, you might notice right now the video is not particularly well centered on my Apple monitor here. And that was actually a thing I noticed with this monitor. For some reason, if I have the video centered well on most of my other monitors, be they LCDs or that Commodore 1702 that I showed in the first video, it tends to be offset to the side on this Apple monitor. I don't know if it's because this Apple monitor is badly tuned, but I actually kind of recall from Apple monitors in the past that they tend to just have different margins than other monitors. And they do not have a horizontal position signal. So one thing, just as a complete off-topic thing I did with the CPU, is the CPU actually has a small amount of built-in EPROM, EEPROM, so electronically erasable and programmable memory, that's program accessible, so you can save between power cycles little pieces of information. So one of the things I did is I added a little switch, this little try me button from something, and by clicking it, I can fix centering issues. I have you can see I have 6 possible positions I can go through. And when I get it where I want it, if I hold this for 2 seconds, and then let go of it, if I power cycle this, it remembers where it was. So I just wanted to show that off. I'm proud of it. Anyway, where we left off was on a cliffhanger about how I demonstrated the code that showed how every 8 cycles in the high-res mode, it's actually less often in the lower-res modes, I have essentially, this machine just essentially counts whatever the number of characters across the screen is. It counts that over and over again, adding each line to an original offset. So for instance, the starting address of the first thing you see on this plate, the test plate in here. There's actually 2 test plates. There's the pterodactyl that's on the screen right now, and there's the text plate that's coming up in a moment. This text plate starts at address 0 in this ROM chip. It's about 16K long, a little short of it. And then the pterodactyl starts at the 16K mark in the ROM chip. So when it's displaying this, for instance, in the 64 column mode here, first line, it starts at 0, reads 64 bytes. Next line, this is a graphics mode. It reads the next 64, blah, 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 down through the cycles. And essentially all the CPU does is just keeps adding 63 for every line. It takes 2 machine cycles to add a 16-bit number. Then it simply outputs it here. That puts it on the ROM's address lines. And then, mysteriously, as you saw, because there was nothing in the code about it, a shift register load is generated, which takes the data output from this chip and puts it into the shift register, and from there it's shifted out. The other mystery that I kind of went down a premature dead end with that in the last video is you notice that I can do different resolutions. So here I have a 40 column resolution. That's the 64 column resolution. There's that comically low 20 column resolution coming up, etc. As you know, as you might know, that the pixels are just different widths in these, and different widths means different pixel clocks. And that is what is displayed on the oscilloscope right here. For instance, this is the 32 column mode, which, remember, the source pixel clock is the CPU clock, which is 12 megahertz. That is divided up, so in 32 column mode, which you have again, see, this is the source clock, 12 megahertz. This is the 6 megahertz clock. This is an 8 megahertz clock used for the 40 column mode. You notice that actually the thin pulses are the positive going pulses are the same width as the source clock, and the low ones are lower. That one's special. It has a 3366 duty cycle instead of 5050 like all the others. This is the super low mode, is a divide by 3 clock. 1 2 3 was 2. Now we're back to 1 2 1 1 2 1. 1 2 1. So yeah, as you see, these spikes the same height, then the low is twice as long, high is the same height, low is twice as long. So this has that unusual duty cycle. So how do we generate that? Well, for that we use a magical thing called a gal. So what is a gal? Let me bring up the data sheet over here on the screen. A gal is a programmable logic device which is a descendant of an early device called a PAL, for a programmable logic array, that, if we scroll down in the data sheet here, internally looks a lot like a ROM, say something like a ROM chip. So it's essentially a large grid where you have input pins and you have output pins, and it's electrically programmable. So essentially all these intersections in a PAL, they're called a fuse, and it's still called fuses when you're programming gals. These fuse junctions can be essentially, under programmatic control, either connected or not connected to these input gates that are on the output logic. And so each input pin is actually connected to 2 points, essentially, on the fuse map. You see there's an inverter right here. So the state of the input pin is either directly transmitted to a line, or it is inverted and transmitted to a line. So you can see every input pin connects to the grid, 2 wires on the grid. And also the output logic has these feedback pins, which are also connected to the grid, so it can actually see its own output. Now, every one of these lines is essentially a stack. It's like a multi-input AND gate. Sorry. Yes, it's a multi-input AND gate. So there's the decision-making logic when it's in simple combinatorial mode is if you want, let's say you want to decide whether the output of this pin is a 1 or a 0. So the state of the input pins will essentially be, at the barest level will be if all the pins that you've connected to are a 1, then this will be a 1. If anything is not, it'll be a 0, it'll fail. So, for instance, if you want the output of pin 19 to be a 1 when both pins 2 and pins 3 are a 1, you would basically connect one of these input gates sections to basically this point in the grid and this point in the grid. So when it is evaluated, it'll go through and very quickly, like instantaneously, check. Oh, I've got a 1 here, and I got a 1 here. No, but if it's 1 here, no 1 here, you don't get it. Now, each one of these output gates has multiple sets of these AND-based decision wires. So let's say you wanted to do like an XOR function, where if you wanted the output of this pin to be a 1 if pin 2 was a 1, or if pin 3 was a 1, but not if both were, and not if neither was. You would actually use 2 of these wires, and you would specify, for instance, the first equation where you want it to be the same as 1, you would say you want it 1 but not 3. You would connect that wire to the non-inverted version of 0 and the inverted version, non-inversion of pin 2, which is 0 here, and then you would connect it to the inverted version of 3, which is number 5. So the equation would be evaluate as true if 2 is true and 3 is not true. And then on the next wire, you would put, you'd reverse it. You would take the inverted version of 2 and the straight version of 3, and that one that would evaluate the opposite way. If 2 was true at the same time as 3, it would fail. So basically you have the AND lines which go across the grid, and you have a varying number of OR possibilities. So if you're all familiar with having to do, say, address selection logic or decoding with a CPU, this would obviously probably immediately ring a bell as something that would be extremely useful. So, in simple combinatorial logic situations, gals alone are extremely useful. But how does that help us with this? Because we're not looking at instantaneously being able to look at 2 pins and somehow get a, change the frequency of something. And that's when we get to registered mode. All right, quick rundown on registered mode. So registered mode adds a new layer to the combination logic that we were talking about before. So in registered mode, you have inside of each box, you add a flip-flop, and that flip-flop is clocked by an input clock. Pin 1 becomes a dedicated clock cycle. And what that does is it means instead of the state of the output pins, combinatorial mode, it basically changes pretty much instantaneously. I mean, every 15 nanoseconds or less, whatever the speed is rated at. Instead of it changing instantaneously, it changes based on the rising of the input clock signal. So that means that you can change the frequency of something by creating a state machine where at the state of an output pin will only change at some division of an input clock. So I'm going to show you quickly. I'll try to keep this as brief and not confusing as possible, although good luck with that. How I do it. So first off, I want to mention real quick, if you've ever talked about programming gals, the software that's going to come up is a piece of software called WinCupl. WinCupl. I don't use it. I'm not saying it's bad. It's probably excellent. The problem with WinCupl is essentially it's a 20-year-old piece of software written for an ancient version of Windows, and it's extremely difficult to get running on more modern OSs, and is very buggy. So if I was doing something complicated, I would still probably want it. I have actually gotten it to work inside of Wine. I could not get it to work directly on my Linux box. Oh, sorry, on my Windows box. But what I'm using instead is a piece of software called GalaSam. Now, GalaSam is essentially an open source clone of an old piece of software called PalaSam, which operates at a much simpler level. So WinCupl has some nice features, like you can take a group of pins, and like I mentioned, how if you want to do it for address decoding, you can take a group of pins and you can abstract them as if they were actual hexadecimal addresses, and you can write an equation where instead of directly specifying the state of the input pins, you can express it as a hexadecimal number and say, have this output pin be true based on this number that applies to a group of pins or whatever. But honestly, I've found the PalaSam syntax not that hard to wrap your head around, and there are tools out there that can help you. If you can feed a state table to it and it will digest it into an equation. You can do what WinCupl does manually, and that's what I do. So with that in mind, let's take a quick look at what I'm doing first off. So on my board here, there are two gals right now. There's this one over here, which is running as a constantly running clock divider. And what comes out of this clock divider chip is, you see, the source of the clock is this 12 megahertz crystal, which is fed into the MCU. The MCU can internally drive a bare crystal. The fuses on the MCU are set so the clock that it derives for itself can be fed out onto a pin, which is right here. So you see I have this white wire going to the clock input pin on this gal, and this divides it up into various clocks. These wires going from here into this gal can use it, for the various clocks you see on the screen. This gal does the shift register state machine, which I'll get to for a minute. So first, let me show you real quick the code for the clock divider. So this piece of code is basically based on standard, there's an example here in the GalaSam documentation of a 4-bit counter. This is directly derived from that. Now, counters are pretty easy to implement in counters are pretty easy to implement on gals. Basically, you set some pins up in registered mode. That's what the R here is for. And the lowest hanging fruit is just a divide by 2 clock, where you just take a single pin, you register it, and then the equation, ignore this reset part for the moment. The equation here, see, this is the negation. Remember when we were looking at the grid, you can take either the direct value of a pin or the inverted value. Well, this is taking the inverted value of itself. Now, in this syntax, if there's non-inversion here, because I could invert the output state, but with it normally, this will be 1 under these conditions. So the condition here is, remember the negation here, this will be 1 on this tick of the clock if excuse me, if this pin is not a 1. So basically, if this starts out, if this is 0, make it a 1. And of course, if it's a 1, it's going to be a 0. Now remember, a clock tick, tick of a clock is an up and down cycle. It's not just each bump. So let me go ahead and I will hook the oscilloscope up to that pin. That's our divide by 2. And you can see on the oscilloscope, this is the input clock. This is a 12 megahertz clock. For every 2 peaks we have up here, we have a single peak down here. And that is because on the first rising, on the first rise here, it sets this high and it falls. Remember, that would be a whole clock cycle. And then on the next rise here, it sets it low. And so for the next clock signal, it's low. So that, any device is going to look for bang, 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 and it's looking for peaks. It's going to see half as many peaks in the same time period, so voila, divide by 2. Now, where this gets a little tricksy is, you see, again, ignore the R sets. Now, this says a 3-bit counter. That means it can count up to 8. And I'm going to leave it as an exercise to the reader. Again, I recommend go ahead and download Gallisam and look in the Galler directory. And that's where all these examples are. It also comes with example files. Explore the examples and work out on a piece of paper how those inversions work, and you'll be able to see how it is that this cycle works. So just by doing a counter, you can do divide by 2, divide by 4, divide by 8. If you want to divide by 16, you could add another bit. Now these get more complicated. Basically for every cycle you need to add another plus, because you need more ors, but whatever. But I don't just divide by even numbers, because I mentioned, remember my clock is 12 megahertz. This is an 8 megahertz pixel clock. So how do we get an 8 megahertz pixel clock? Well, this is where we're combining here the stateful logic with the direct combinational logic by, first off, the R set here is I am resetting this timer when it gets to when it counts to 6 clocks instead of 8. So if I move this input signal here on the oscilloscope to here, you'll be able to see on every 6th tick, this goes high. Now, how that works is it's held high through tick number 5, essentially. And then when tick number 6 happens, remember the gal evaluates state at the start of every cycle. So this being high makes our set true instead of false, like in the equation. And that means it will reset all of the clocks to 0. So, I mean, if I move this and look at pin 2, for instance, you can see that doesn't have an even duty cycle because this is the, oh no, see me bumping around here. There we go. This gets reset, so it ends up essentially as a 3360% duty cycle divided by 6 clock because it doesn't get to do its next peak at the right moment. And likewise, if we look at the next pin down, you'll essentially see a mirror of it. End up pretty much the same. If I do the slope differently, you can see it. That, this would normally go a tick this long and a tick the same length. But because it's reset at 6, it's not liking those probes on there. Sorry about that. So, having it divide by 6 means 6 is evenly divisible by 1.5, and it's a 1.5 divide that we need to get an 8 megahertz pixel clock out of 12 megahertz. So you can see in this equation right here, one thing that's on the board here, if you look carefully, the input clock here, there's a tiny little metal jumper that's also connecting that. See, there's clock, and then there's CL, which is the next pin down. The input clock is also being fed into one of the combinatorial pins. And so these 4 lines basically specify, based on the state of the registers and the polarity of the clock signal, 4 intervals inside of the 6 inside of the 6 count in which the clock should be up. So if I go ahead and drop the probe on that one, come on, behave. Oh, that's what, there we go. Wrong one. Watch out for unshielded wires. So now if we look at the probe, at the scope, you will see the high peaks are the same size as the high peaks here, but there are 2 low periods for every high. So the 8 megahertz clock is a 3360% duty cycle instead of 50-50. That's fine, it works. You can't get a 50% duty cycle without doing some analog tricks out of clock division, or do it using a PLL or something. So that's how we derive that. So that's how all the pixel clocks that are in work on the display here are derived from the single clock, just by using divisions on the on a single gal. Now this last thing down here, so you see this basically supplies, this is a divide by 2. I use the register directly as a divide by 2. So that's a divide by 2 output. There's point, which is that divide by 1.5. There's a divide by 3, and there's a divide by 6. A divide by 4 would be useful, but I can't get a divide by 4 unless I add another register that would work asynchronously, because of course this gets reset. So but that's fine. I don't really need to divide by 4. This one down here is I made this chip capable. I was thinking of if this was used in something like a Z80 based machine or something, a computer. This could be the main clock for the computer. I would, by setting the state of these input pins, see fast and odd, you'd be able to select what clock comes out of an output pin, which is what it does. That's not implemented in this. This is just statically supplying clocks over here now, but that might change for the next phase. So let me move some stuff, and I will show you what the other gal does. So, sorry, I had a little thing we had to take care of. The one thing I've moved since the last shot is I've moved the probe that we were looking at the outputs for the system divider clock over to the this chip, the video shift register driver. It actually does more than that, but what we're selecting here is the clock output, which is fed into the shift register over here. So you can see when we switch modes, we're in 32 column mode. When we switch to 40 column, you can see that we're selecting different clocks. We were in the divide by 2 before, we're in the divide by 1.5 now. When we switch again, we're going to have the 1-to-1 clock, etc. So the way this is done, so let's go ahead and look at the code for this here. So this is the code for it. You'll notice we also have an 8 count here. Let's ignore that for the moment. And the first thing we're going to look at is this. So CL out is the pin that's going to the shift register, but you'll also notice there's a white pin looping it back into the gal itself. Now what that is for is the gal, when it's in registered mode, it always takes its clock on pin 1. So what if we want to have different clocks and we want to be able to base registered actions like the time, like this particular counter, based on a different clock? Well, we can either switch the clocks externally, which I might redo this so the clock selection that's already built into this actually just feeds a single clock line to this. But for now, I went ahead. We have 2 wires coming from the MCU here that can select. So they're like, so we have 4 clocks coming in. We have over here on the code, we have full, which is the full 12 megahertz, 30, which is the divide by 2, 40, which is the 1.5, and super low is the divide by 3. There's also these 2 modes, 8 and fast. 8's a long story, which allow it to select 4 different clocks settings, and whatever binary combination is set here picks a clock from one of the 4 input pins and feeds it to both the shift register and feeds it back into the gal, so the combinational stuff can happen. So just for fun, say I were to yank one of these out, you'll see suddenly I'm using the wrong pixel clock for that mode, because the pin just went high. If I jam it back in, wrong pin. Oh, there we go. It selects it correctly. If I pull out the other one, we'll have different symptoms. Probably not in this mode. Come on, come on, go to the next mode. I want to see something bad. No, actually, yeah. See, it's using the divide by 2 instead of the divide by 3 that it's supposed to. Sorry, divide by 2. 1.5. Oh my God, I can't do math. All right, so that's how the clock is selected. Again, that's a function I might actually pitch over to just connecting these over to the other gal and feed a single clock into it, because I actually have a couple other things in mind for this, but I'll get to that. But that's how we switch between clocks. Now, remember earlier, way back at the beginning, there was the standing question: how the heck am I generating shift register loads without the MCU sending any signal for it in the code? Well, if we go back and look at the code, let's go ahead and go back to that the thing I was showing you. There's a line in here: start the shift register counter. What that is this yellow wire right here. It sends a during an active line, it goes low. It's normally high, it goes low. When it is low, that is the time in which shift register pulses should be coming out. So, for instance, if I go ahead, we've got the trigger on this guy. So let's go ahead and put the trigger on this pin, and we'll take this sense pin, and this red wire here is the shift register output. So you can see, go ahead and clock this up a little bit. When the shift register goes low, sorry, when that line, the start the shift register counter, goes low, we have shift pulses. If I change the slope, so you see it goes high, we no longer have shift register pulses. So that will only generate shift register pulses when that goes low. And if we look at the GAL code, shift register loads are happening, so this is this 8, remember we have 8 bits, 8 clocks per 8 clocks per cycle. The shift register goes high on it goes low on the 4th cycle. It goes on the 4th cycle when that wire is low. So, again, that's why the clock free runs. The clock just free runs all the time, but it will only generate the pulses when it's low. Now, the other thing you might think, though, is if it's free running, how do I know when the shift register pulse is? Because if I just guess, or if I'm misaligned, I might try updating, if I update the address lines right when the shift register pulse is happening, then I might get garbled output because the output from the memory won't be in a stable state. How we take care of that is I've done some more cleverness with registers, which is I've taken one of the the registered pins, and I've created it so on the clock pulses it's set to whatever that pin is. So if I move the trigger, so we're looking at that. Let's see, VSET is the one over the shift register out. If I set that to this, you'll see it'll basically look the same, except, oops, oh no, wrong button. It actually lags because it's registered, it actually lags that one slightly. What is that good for? So you notice that even though this free runs all the time, there is a reset. And what the reset does is, this is called VSET. So our set when ActVid goes low. So remember, it goes low. All high, happy, it goes high, it goes low. Reset goes low, except you'd say, well, if it was just combinatorial, then that means reset would be held down the whole time of the active line and there'd be no pulses. But RSet is activated when reset goes low, but the previous state of ActVid was high. So essentially what that is doing is that is creating what's called a one-shot. So if I look at if I move the probe over to that signal, let's see if I can get that a little more on the screen. So you see there's a very brief pulse that happens that see, it's very brief. It's less than a clock cycle, but it's enough that it changes it over between this and that, and at the same time, the counter is reset. So if I were to, let's say, go onto one of these cues, it's difficult to see because I don't have a memory oscilloscope, so I can't remember anything that goes this way. It's one of these things I should probably think about investing in one of these days. But for instance, you see it's a nice square wave, except here, this was low going into this, so we ended up with a long clock pulse here. It means that it resets. It basically changed the phase of this. It held a long cycle. There it is again. See another instance of where it's a long cycle and then short cycles. That means that in the code, that's a beautiful version of it. Long cycle, short cycles. That means we can simply, by aligning our code correctly, saying we did this. Remember, we're counting, we're bit banging anyway. We have to make sure that we set the rows, set the address every 8 clocks. We just need to make sure that we stay in phase, because we're going to know that it's going to be on the 4th tick that it's going to shift register. We just need to make sure we arrange our code in every section so we don't land on top of the shift register pulse. And yeah, that's how that is handled. We basically get, and another way that could have done this, I could have done this without the one shot. I could have simply run another wire from the MCU that when to reset the clock explicitly. But by using this one shot technique, I only need one wire and it happens automatically. I just say you're shifting or you're not. And I actually use this for 2 functions, which is, you notice I have, I also reference this VSET state on the shift register equation. And the reason that is because I discovered that if I happened to turn on the shift register shifting when the counter was at 4, it would actually prematurely go ahead and fire a shift register pulse before it reset the clock. So you'd get a little shadow of garbage at the beginning of the line depending on the clock phase. So you'd end up with some junk over here. By referencing this VSET, then it will suppress a shift register pulse under that circumstance. So the one-shot register actually kills 2 birds with 1 stone. Now, the last bird I'm going to kill with this stone. So, if you recall the beginning of this, I don't know if any of you watched it. I don't blame you if you didn't. If any of you guys watched this, I was talking about this is building a video card for like an S100 machine or something, but I'm at the point where I need to interface this to a computer. But it occurred to me that Um, with this state machine right here, this could actually be my ideal first case for interfacing this. Might actually be a 6502 based machine. Um, so let me bring something up on the computer, and I'll be right back. All right. Um, so up here on the computer screen, I have a little page that demonstrates how the bus timing on the 6502 CPU works. This is going to be kind of deep for people that aren't familiar with the specialness of the 6502, but I'll give you the very short version of it. The 6502 and derivatives of it was the CPU that was used in many home computers of the 1970s and 1980s, like the Apple II, the Commodore 64, VIC-20, Atari machines. Derivatives were used in video game consoles, whatever. There's a reason why that CPU, well, many reasons, but there's a simple reason why that CPU turned up so often in home computers that were intended to be connected to a television set, and otherwise were low parts count. And the reason for that is the 6502, somewhat uniquely, has this very predictable bus cycle where the CPU basically only uses the bus half the time. So on its input clock cycle, remember a clock cycle goes high, goes low, goes high, goes low, goes high, goes low. The 6502 only uses the bus when the clock cycle is high. It never touches the bus, other than the older versions will start outputting addresses. It never tries to do a read or a write when the clock cycle is low. Now what that means is if you're a clever designer, you can take if you can run your memory essentially at twice the speed of the CPU, you can interleave reads from a video device with the CPU without needing any wait states and without really basically slowing the CPU down at all. That makes it, again, very good for that particular application. So when I designed the state machine to automatically generate the shift register loads, it occurred to me that I could use the same state machine to generate a clock that would be suitable for clocking a 6502 on the opposite phase from when the video hardware needs the clock. So I'm going to leave the trigger pin here on remember our one shot that resets the clock. And I'm going to move this pin over to this right here where I've got another blue plug. And this right here is what I'm calling the phi clock. So if I look at our code, phi here is phi is activated one cycle before the shift register output and lasts twice as long. So basically, here I'll move this briefly. So if I plug into the shift register output, oh, come on, be nice. Well, actually, this is one of those things where I kind of need to get my triggers. So take my word for it. if I had the, I'm too lazy to wire up the trigger pin. Basically, the shift register load would be the second half of each of these pulses. So and you notice that's low going. The shift register pulse is low going. I actually have right now the memory output enable connected to the phi clock. So if I were to yank this pin out, you'll see I get junk on the pin. And if I anchor it, if I anchor it positive, I'll actually get nothing. That is basically, and if I trigger it positive, then you'll see it all go. This means that I'm essentially only using the memory during this brief cycle, which is only a quarter of the 8 clocks of the pixel clock. So even at 12 megahertz, at least the output enable is fast enough that I can transition. I can give the memory to it, get the pulse, let this go. Now you notice that leaves 75% of the cycle high. And this is also, the entire cycle between the pulses. That will be, depending on which CPU clock we're running, if we're talking about the 80 column mode, the 40 column mode, that's going to be a 1 megahertz tick. Remember, that's the 1 megahertz CPU memory bandwidth essentially we're dealing with. So my plan is I'm going to get, maybe I should have an unboxing. I have a big pile of stuff I ordered, which includes 6 breadboards. I'm going to lay those all out, and I'm going to essentially build a Commodore style computer on the breadboards that uses, I have some memory chips, which are 70 nanoseconds, which should be fast enough, that we're going to have 64K of main memory shared between the video processor and the CPU. And the CPU will get this part of the phi clock. Now, remember that thing about the having to reset the counter? Well, the same deal applies with the CPU, and you'll notice that sometimes, you see, we were high here, low in, low out. If I look at the equations, the fact that this starts on the third tick, essentially, we're never getting shorter than 2 of the 8 clock ticks. Now, what that essentially means is there is no contention. It should ride through. As long as the 6502 is able to essentially deal with once in a while doing 1 tick at, let's say we're running at 4 megahertz and that happens, at the 8 megahertz pixel clock and that happens, that means occasionally you'll get the CPU for 1 tick will run at 4 megahertz instead of 1 megahertz. But the CPU I bought is rated for 14 megahertz. So as long as the memory bandwidth is enough, which I see no deal breakers, we should be able to basically make a computer that will run exactly at the speed of, say, like an old Commodore 64 or PET or whatever. And in fact, because of this cycle, I could actually add a turbo mode where I add a second clock tick, where we don't, the display system doesn't need it, but we could just drop this down again and have it run at 2 megahertz instead of 1 megahertz at the 40 column mode. Might even, this is where, done the math, and we might actually be able to get away with running it as fast as 8 megahertz. But this is where the breadboards are going to come in. So that is the plan. We have, through the magic of gals and some actually pretty simple state programming, we can take one clock from our brain dead little MCU and turn it into a complete clock generator for a small computer. Now, like I said, I may, because we've used up basically all the input pins and such on this now, I will probably go ahead and get rid of this 4-pin lash up and just move the speed control pins over to here and feed it a single pin, and that will also free up one output pin that I'd be able to use if I need like another contention pin or something. I figure I'll probably be a couple more gals before because I'm also going to need like some address decoder gals and such before I'm all done. But I think I should be able to build essentially a Commodore PET style machine, except this machine will also be capable of doing high-res graphics with a couple more gals. And the other part that we'll definitely need is there will have to be some buffers that can tri-state. So, because remember, these are outputting an address all the time, and there's no tri-state pin on the MCU. So I'm going to have to use some like 244 or 245 buffers on these, and those will switch based on the pi clock. In fact, that's actually what I'm most worried about with the timing, is any delay induced by buffers, because I think the memory chips themselves are going to be fine. Now the 6502 CPU I'm looking at, which is the Western Design Center 65CO2, it actually has a tri-state pin on it, which is why if you look at the, like say the Commodore PET schematics that I showed the other day, you'll generally see 1 and 4 MUX chips, 1 and 2 MUX chips used, where you'll have, for like a 16-bit address bus, you'll have 4 chips, and each is 4 bits wide, so you'll have 4 bits from the display address generator and 4 bits from the computer coming into these, coming into one side of the chips, and then a single 16-bit coming out to the shared memory on the other side. I think because the 65CO2 chip has a tri-state pin on it, I should be able to get away with just using a buffer on this and then manipulating the tri-state pin on the 6502. So I'm hoping I may actually essentially be able to get a functional Commodore PET clone down to about a dozen chips. So that is where this is going next. I think the video generation system is pretty much ready for its next test. So I think maybe if anyone's interested, I might do a quick unboxing of all the parts I bought for the next phase. And maybe if anyone's interested, I don't know if anyone would be, I could do one of these top-down videos of, I'm actually going to keep this test harness put together and, replicate on the new boards, so I can go ahead and test further revisions of this MCU code in isolation instead of on the fully built out board. So if anyone's interested in like an initial population build of the 6502 project, drop me a line in the comments. And again, I'm sorry my production values are so bad. Clearly I need to invest in some better equipment and learn how to act and talk and speak and all that other stuff that YouTubers need to do. Join a Toastmasters club perhaps. But anyway, I think I've covered gals as well as I know how, which isn't that great. Thank you for watching, and happy 2021, everybody.